Section 10.9 is the last section we're going to do in Chapter 10. This is the last section that's going to be on your exam 4. So this is the convergence of Taylor series, and we're going to start out today with picking up where we left off last time. We're going to use the substitution method to find the Taylor series at x equals 0 for the function e raised to the negative 12x. In order to use substitution, we have to start with what the Taylor series is for e to the x. You should have this written somewhere on your notes from last time or have it on your series test sheet. E to the x is equal to the sum n equals 0 to infinity of x to the n divided by n factorial. So we start with the function that we want to find the series for, and that's going to be e to the x equals negative 12x. In order to find the series for this, I'm going to replace what with what. In this series, what gets replaced? I replace x with negative 12x. So this becomes negative 12x raised to the n divided by n factorial. Now you don't want to leave it like this. You do want to clean it up. This is going to be equal to the sum n equals 0 to infinity of negative 1 raised to a power of n times 12x raised to a power of n. That way you can see that this is going to be an alternating series. This is pretty straightforward. In example 2, we're asked to find the Taylor series for 6x e to the x. I already have the series expansion in green up here for e to the x, so I'm just going to write down what it is we're going to find. We're going to find 6x e to the x, and that means that I'm going to multiply my series for e to the x times 6x. Well, e to the x is the sum n equals 0 to infinity of x to the n over n factorial. This is the series representation of e to the x. So when you have a constant or a variable multiplied by a series, an infinite series, we can bring that constant into our series representation, and that's going to give us the sum n equals 0 to infinity of 6x times x to the n over n factorial. And you don't want to leave this like that with two x's there. We can combine these into one single term simply by multiplying the bases together using properties of exponents. So this will be the sum n equals 0 to infinity of 6 times x to the n plus 1 over n factorial. And that would be our final answer. Example 3, we're asked to find the Taylor series at x equals 0 for the function shown below. I've gone ahead and put in what the series representation for sine x is, but we've got to figure out what are we going to do with this, because that's pi over 4 times x. We're going to start solving this problem by writing down our function. This is going to be x sine of, I'm going to write pi over 4 times x like this. So that's going to be x times, and then the series representation for sine is going to be the sum n equals 0 to infinity of negative 1 raised to the n times, in place of x, I'm going to plug in pi over 4x, and that's going to be raised to the 2n plus 1 divided by 2n plus 1 factorial. Now, can I clean this up? Well, yeah, I can. But what do I need to do first? I've got to take this x and I'm going to move it inside this argument here. And that's going to allow me to rewrite this as the sum n equals 0 to infinity of negative 1 raised to a power of n. So now what I've got is pi over 4 raised to the 2n plus 1 times x raised to the 2n plus 1 times x, and this is the x that I moved from the inside here, divided by 2n plus 1 factorial. There's two things going on here that I want to address before I'm ready to say this is my final answer. One of them is I've got a fraction within a fraction. I don't want a compound fraction here. And the other one is I've got two terms with the same base that I can combine. The way that I can address that compound fraction is to just use the distributive property of exponents and kick that 4 into the denominator. Do you remember that we had a distributive property of exponents that says if you have a fraction raised to a power, that's the same thing as the numerator raised to the power over the denominator raised to the power. So that's going to allow me to rewrite this as the sum n equals 0 to infinity of negative 1 raised to a power of n, and then my constant term is just going to be pi raised to the 2n plus 1, and my x is going to be raised to what power? 2n plus 2, because I would take the 2n plus 1 plus the 1 from that last x there. And then in the denominator, I'm going to have 4 raised to the 2n plus 1 times 2n plus 1 factorial. And this would be my final answer. The next thing we're going to talk about is Taylor's theorem and how it's going to lead us to a remainder theorem. If f and its first n derivatives are continuous on a closed interval between a and b, and the nth derivative is differentiable on the open interval between a and b, then there exists a number c between a and b such that f of b can be written as f of a plus f prime of a times b minus a plus the second derivative at a divided by 2 factorial times b minus a. What do you notice about this? This looks an awful lot like something else we've seen. Remember our Taylor polynomial where we said our first term was going to be f of a, and then the next one would be f prime at a divided by 1 times x minus a plus the second derivative evaluated at a over 2 factorial times x minus a squared plus the third derivative evaluated at a over 3 factorial times x minus a cubed, so forth and so on. Look at what I have written in blue and what's in black. What is the difference there? There's only one letter that's different. Everything else is the same. We've replaced x with b in the Taylor's theorem. The conditions that have to be satisfied is that the function has to be differentiable and continuous on a closed interval from a to b. So on this closed interval from a to b, we are continuous and differentiable. And then on the open interval from a to b, there exists some number c between a and b. I don't know where it is, but it's somewhere in between. So that we have all of these terms where we are replacing x with b in our Taylor series, so that if I add up a whole bunch of terms and then I get to this last term right here, instead of evaluating the derivative at a, I'm going to evaluate that derivative at some constant c, keeping the b in place of x. That's going to give me a Taylor polynomial. This last term right here is what we're going to call our remainder. So this is Taylor's theorem. When we apply Taylor's theorem, we usually want to hold a fixed and treat b as an independent variable. Taylor's formula is easier to use in circumstances like these if we change b to x. Here's a version of the theorem with this change. So that last term I said right here is going to be our remainder. And in this version, that's what they're going to call this, where r sub n of x, that nth term there for the remainder, is going to be that last derivative, n plus 1, evaluated at c, divided by n plus 1 factorial, x minus a to the n plus 1, for some c that's in between a and x. This is Taylor's formula for the remainder. When we state Taylor's theorem this way, it says that for each x that's in our interval of convergence, the function can be written as an nth degree polynomial plus some remainder. Notice for the remainder, we use n plus 1 here, and that's called the nth remainder because our polynomial stops at the nth term, so that would be an nth degree polynomial. If the remainder approaches 0 as n goes to infinity for all x's in the interval of convergence, we say that the Taylor series generated by f at x equals a converges to f on that interval of convergence, and we would write this for our Taylor series. Now we can use this remainder to estimate an error. If we're using this formula, the Taylor polynomial goes out to n equals n, whatever number that's going to be. The remainder is just going to be the next term, and that would be the n plus 1 term. Here, that subscript of n is going to be equal to the degree that we're plugging in into our series, and for the remainder, we're using the n plus 1 term. It would be the very next term. And I'll show you how we can use this to estimate the value of a function at a particular value of x using the polynomial with the remainder theorem. For example 4, we're asked to estimate the error if the third degree Taylor polynomial is used to estimate the value of sine x at x equals 0.8. We already know the Taylor series representation for sine x. That's going to be the sum n equals 0 to infinity of -1 raised to a power of n times x to the 2n plus 1 divided by 2n plus 1 factorial. And this is a third degree polynomial, and we want to know what the error is. So we have this theorem that says we can take the function and say that it's equal to a polynomial plus some remainder. That remainder would be the error. So using this Taylor series for sine of x, we know that if n is equal to 0, we're going to get x. And when n is equal to 1, that's going to give us a minus x to the third divided by 6. And if I were to expand this out, that next term that I would get when n is equal to 2 would be my remainder. So when n is equal to 2, that's going to give us a positive because n is squared. X to the 4 plus 1 is 5, so that's going to be x to the 5th over, and then that's going to be 5 factorial, and 5 factorial is 120. This term right here would be the remainder for the third degree polynomial. So to find the error at x equals 0.8, all we're going to do is we're going to plug in a 0.8 in place of x in the remainder. And when we do this, we're going to get 0.8 raised to the 5th divided by 120. And that's why God gave us calculators. If we go to our calculator, we're going to see that this is 0.002730667. That means that the absolute value of the error is going to be less than or equal to 0.022730667 if we have a third degree polynomial. So the steps that we went through was we found the next term in the polynomial. That's what we did. We looked at the polynomial, we find the next term. That next term is our error. Once you've identified what that term is, you're going to then plug in what they give you for x into that last term and to get an upper bound on your error. It's not going to tell you what the error is exactly, it's just going to give you an upper bound for the error. So step 1 was to find this term, step 2 was to plug it in, and then step 3 is to write up your answer. The final answer is going to be the error is going to be less than or equal to 0.0227. And that gives you the upper bound for your error. And this wraps up section 10.9.